4 lessons down. I'm going to start trying to push them further as we go along. We're also probably going to finish this section of work relatively quickly. So after we do a revision quickly of the feedback system, we're going to do the pancreas. After the pancreas, we're just going to do the movement of water and salt through the system, and then we're going to start reproductive strategies of plants and animals, but majority animals as well. So in there, I'm going to be teaching you a whole bunch of stuff. I really wish I could do this in a classroom. It would be so much easier, but let's see if we can get this done. All right, so I noticed that you guys did struggle a little bit with the feedback mechanism, so let's quickly go over it. I found another set of slides that another teacher had set, and maybe they just laid it out prettier with some colors, and maybe that will help you guys. But it's also the same thing, just in different words to a large extent. So let's begin. Okay. So negative feedback mechanisms are responsible for maintaining homeostasis. So if you remember what homeostasis is, it is the, I wrote it down somewhere over here, but it's everything that needs to be maintained, and there's a whole bunch of stuff that needs to be maintained in the body itself. Okay, so homeostasis is the ability of the body to maintain a constant internal environment, irrespective of changes from external environments. So now let's look at the basic. We have any changes in the level of hormones in the blood is reported to the endocrine gland. Okay, so the endocrine gland itself can be a whole range of things, whether it be cells in the pancreas, can be the pituitary gland, it can be the gonads, it can be the thyroid, it can be the adrenal glands, a whole bunch of different glands. In other words, information is fed back to the gland. And I've got some really nice sort of visual things that you can have a look at. So the endocrine gland then does the opposite of what is happening to return to the level normal levels to normal, and this is the negative part of the negative feedback system. So something has happened, we're taking it to where it originally was, and that is a negative feedback system. It would be easier to explain using a part of an example. If the level of a certain hormone were to increase, the information is reported to the gland. The gland reacts by reducing the secretion of that hormone, and the gland is doing the negative of what is currently happening in the body. This would reduce the level of the hormone. This means that the level will return to normal and homeostasis is met. Okay, so let's have a look at thyroid stimulating hormones. I'm going to use this as a good example for you guys. So, when the level of thyroxine is too low, the pituitary gland secretes more thyroid stimulating hormone. The thyroid stimulating hormone then stimulates the thyroid gland to secrete more thyroxine. In this way, the levels of thyroxine in the body increases to normal. And when it increases to normal, it inhibits the pituitary gland from releasing more thyroid stimulating hormone, which will stop the thyroid, which will stop the production of thyroxine. So remember, there's always a negative feedback. So something happens, and then something has to inhibit one of the endocrine glands. When the level of thyroxine is too high, the pituitary gland secretes little thyroid stimulating hormone. And this is because you now have too much thyroxine, and this thyroxine is actually inhibiting the pituitary gland. So the reduced secretion of thyroid stimulating hormone then causes the thyroid gland to reduce the secretion of thyroxine. In this way, the level of thyroxine is lowered to normal in the body. Okay, so there's some see what it looks like in reality. So on the right hand side over there, we have a stimulus, the sensor, the control, and the effector. Okay, and then it goes back to the stimulus as well, and the stimulus then changes how the sensor is going to work. And remember, the stimulus is now changing after the whole thing has happened. So let's jump into, well, let me quickly just go over how I notice it. So I want you guys to draw that little basic negative feedback loop over there on the right hand side, and then let's go through all the bits and pieces from the words that we had earlier. So let's say there is too little thyroxine in your system. Okay, so the stimulus is the thyroxine levels dropping. This is then going to go to the sensor, which is your pituitary gland. This pituitary gland is then going to try and control the fact that there is too little thyroxine. In this instance, if there is too little, it's going to increase the amount of thyroid stimulating hormone. That is the control. Then eventually there is an effector where, as it releases more thyroid stimulating hormone, it stimulates the thyroid to release thyroxine. Now, as the thyroxine increases, it's going to go back to normal, and that normal level is going to become the new stimulus, which then inhibits the pituitary from releasing more. Okay. The same happens if the thyroxine levels increase too much. Okay, so now the stimulus is that there is too much thyroxine in the system. This is going to stimulate the pituitary to inhibit it to a large extent, which is going to produce less thyroid stimulating hormone, or TSH. This causes the thyroid to also be inhibited and releases less thyroxine. When it releases less thyroxine, the body comes to its normal state. And that normal state will then go back all the way and become the new stimulus and tell the pituitary that we have enough, inhibiting whatever was going on. Okay, so let's go back to the left hand side just so that you guys can see. So it says there normal thyroxine level at the top. If you look at the left hand side, it says if the level drops, the pituitary secretes more thyroid stimulating hormone, the thyroid gland is stimulated, more thyroxine is produced, the thyroxine level rises, and we go back to the normal thyroxine levels. And remember that the thyroxine level rising stops the pituitary gland from actually secreting more TSH. So let's do the right hand side of that. If thyroxine level rises, the pituitary gland senses this. The control is that the thyroid gland is inhibited because there's no thyroid stimulating hormone and less thyroxine is produced. Therefore, the thyroxine levels drop, and this will then go back to the pituitary where it says, okay, now we are at normal levels, stop, just stop doing what you're doing, and you're potentially now going to have to increase it. Okay, so I hope this helps you. I'm going to be using, I want you to draw this as well, because I'm going to use it exactly the same thing when we do how the pancreas works. Okay, so things to do. So I please want you to go over the disorders of hypo and hyperthyroidism on page 39 and 40. Just highlight the important bits. Then I want you to do activity 2 on page 40 and 41, please. All right, so do that first, and then have a basic understanding of how the thyroid works, and then you'll continue. All right, welcome back, hopefully from doing that activity. Okay, so now we're going to look at the pancreatic islets, technically it's isle, so islets of Langerhans. Yes, it's a very German sounding name, and this secretes the hormones insulin and glucagon. Alright, so if you're wondering where on earth your pancreas is, there is a picture that I still haven't put on the classroom, but I'll get there later. You can see from the bottom part over there, it has a tiny little label that says pancreas, and it has head and body and tail. So that entire structure over there, which is a very phallic looking structure, is the entire pancreas. Please note that it is behind the stomach. Remember, you don't want the pancreas to be damaged in any way, because if your amount of insulin and glucagon is affected, you're ultimately going to struggle quite a bit. Please also recognize, there's one more thing, that the liver and the gallbladder and the pancreas are all attached by a non-specific duct that goes into the beginning part of the duodenum over there. So please just note that all three of those organs actually have direct connection into the small intestines, which is going to start creating a brand new environment that is going to help. Please also just remember as well that the pH of the small intestine is more alkaline in nature, which means that the pancreas, where she produces sodium bicarbonate, that actually reduces the pH to a large extent. Alrighty, so then the pancreas is both exocrine and endocrine. Let's quickly just remind ourselves what those are. An exocrine releases substances onto a surface, whereas endocrine releases into the blood, and it is both of these. So the pancreas is absolutely both. So in terms of the exocrine, it secretes substance that makes the interior environment of the small intestine more alkaline, as well as also releases a whole bunch of digestive enzymes. Then in terms of endocrine, it releases insulin and glucagon. It's not the only thing it does, but this is one of the main things for matrix specifically. And again, please notice, you'll see that green tube inside over there. You've got the bile duct from the liver, and you've got this tube coming in from the pancreas into the small intestine on the side over there. The two particular hormones we need to learn about are insulin and glucagon. So there's 4 words you need to know off by heart by the end of this. So insulin is able to stimulate the absorption of glucose. So there is too much glucose. We now need to convert glucose to glycogen. Okay, too much glucose, we release insulin, and that converts glucose into glycogen. From glucagon, we can see that it stimulates the conversion of glycogen to glucose. So please also remember that now glycogen is a stored version of glucose. And remember, you don't want glucose running rampant through the system as well, for the simple fact that glucose can actually cause the movement of water quite significantly and can ruin the entire osmoregulation within inside the body. So you really want it to be extremely specific. You can't have too much glucose in the system, and that's why if you eat too many sugary things, you're ultimately going to get fat, and that's because the body is just storing all that glucose that you're not using directly into fat. Okay, this glucagon works on the liver and the muscles. So the muscles and the liver releases glucose into the blood. Now, I've put a picture up at the bottom over here, and you can mainly see, like, it's almost like we've taken a whole chunk of that pancreas and we've just like enlarged it to a greater scheme of things. Right at the bottom, you'd see two names, alpha cell and beta cell. These are extremely important and often do come up in multiple choice and give the correct biological term. So your alpha cells produce glucagon, whereas your beta cells produce insulin. So again, the beta cells, which release insulin, stimulates the liver to, or like the absorption of glucose and the conversion of glucose to glycogen, specifically in the muscles and in the liver. Whereas glucagon, which is released by the alpha cells, they convert glycogen into glucose, releasing the glucose into the blood. So if there is too little glucose, you're going to release glucagon. If there is too much glucose, you're going to release insulin. Okay, so the words, like all the three G's, they suck quite a bit. So you've got glucagon, which is the hormone. You've got glucose, which is the fuel. You've got glycogen, which is a storage version. And then you have insulin, which is also a hormone. But insulin reduces the amount of glucose, whereas glucagon increases the amount of glucose in the system. You can hear I'm getting tongue twisted here. Okay, so this is the negative feedback system of the entire structure. So what I want you to follow is either the red line or the blue line. So we'll do the red line first, because this happens more often in your systems. So first and foremost, you're going to have high blood sugar, which means you've just had a big meal. Remember, you're feeling hungry, your sugar levels are low, your body's now recognizing, listen here, I need to actually get some food in my system. So you've just had a big meal. This promotes the insulin release. And what cell is promoting that insulin release? The beta cells. Great. Okay, sorry, I just had to read my notes again. So the beta cells are then going to be stimulated. They're going to produce a whole lot of insulin. That insulin is released, and this causes will stimulate glucose uptake from the blood. And where does that glucose get into? The tissue cells as well as the liver. But in the liver specifically, we're going to convert glucose into glycogen. When I absorb all those glucose into my tissue cells as well as my liver, the amount of blood sugar is going to decrease quite significantly. If we look at the low blood sugar at the bottom over there, this is when you have not eaten for an extended period of time, or you're working out, you're doing a very crazy workout, and this is going to tell the body, listen here, we don't have access to food. And remember the whole rest and digesting as well. So if you're not resting, your body isn't going to alert you to the fact that you're hungry. You'll know that you're hungry, but you're not actively going to sort out food. It's the whole mind over matter kind of vibe. So when we have this low blood sugar, this promotes glucagon release, which is from the alpha cells in the pancreas. The pancreas then, well, those alpha cells are stimulated. They're going to release glucagon. This stimulates glycogen breaking down and releasing, or breaking down into glucose, and that glucose is going to be put into the bloodstream, and this is going to raise your blood sugar. So the amount of sugar in your system is going to go up and down constantly. So it's a fight constantly where the blood has to move past the alpha and beta cells, which indicates or stimulates them to produce certain things. So now let's look at that previous slide that I was telling you about with a stimulus, sensor, control, and effector. So let's say we'll look at high blood sugar or too much glucose in the system. In the islet of Langerhans, inside of the pancreas, the beta cells are going to be stimulated. These beta cells are then going to be stimulated to produce insulin, or they're going to secrete insulin. Once that insulin is secreted, the glucose is absorbed and converted into glycogen, specifically in the liver. When this absorption has happened and the conversion has occurred, the glucose is going to decrease, and this will be sensed by the beta cells. Those beta cells then will be inhibited or stop from doing their job, and they will then stop producing insulin, which will allow you to bring your levels back to complete normal. So the same thing is if we had too little glucose, that will be your stimulus. The islets of Langerhans alpha cells will then secrete glucagon. This will cause glycogen to be broken down in the liver and released back into the blood. This causes the blood glucose level to increase, and then this is sensed by the alpha cells, which causes the inhibition of the alpha cells as well. Okay. So hopefully that helps quite a bit. Let's look at this particular picture as well. This is, if you guys want to draw this, you're more than welcome to. It's a nice way of sort of understanding what is going on. Okay, so we're going to look at the action of glucagon first. So missing a meal brings the glucose levels down below the normal set point. So you can imagine there has to be some sort of equilibrium. Or there has to be some sort of range where, you know, the body will not constantly be fighting this up and down, up and down, up and down, which it does, but mainly because it just drops below that range where it should be, which causes the pancreas to secrete glucagon into the bloodstream. So if you want your 50%, you're going to write pancreas. If you want your 70%, you're going to say it causes the pancreas, or the islets of Langerhans inside of the pancreas, specifically the alpha cells, to secrete glucagon into the bloodstream. This signals to the liver to begin converting stored glycogen into glucose, and this raises the normal blood blood sugar. Then if we go to the action of insulin, we have eating a meal increases the blood glucose level to higher than normal homeostatic set point. This causes the islets of Langerhans beta cells in the pancreas to release insulin into the bloodstream. This signals to the liver to begin taking up excess glucose and store it as glycogen, which causes the blood glucose levels to drop. Okay, so it goes up and down and up and down and up and down and up and down constantly. All right, and it's not that insane, but it's just, you just need to learn how it works. So if there is some sort of problem, and believe me, there are problems, you're going to suffer from poor or reduced secretion of insulin. So let's just talk about like how your pancreas could be affected that would actually cause this whole thing to go on. So sometimes the pancreas cannot secrete enough insulin because the pancreas has become damaged. So you have a car crash, someone punches you, you stab yourself, you get shot, I don't know, but your pancreas becomes damaged. Maybe you also put dangerous substances in your body. The quality of the insulin produced can also be low. Okay, so it's either being damaged or the quality is just low, so your body's just not producing it properly. Both these cases lead to the inability to reduce the blood glucose levels when it becomes too high. So we're not dealing with the fact of it's becoming too low, we're only dealing with if it becomes too high. When people are unable to control their blood glucose levels, we can say that they suffer from diabetes mellitus. You need to know that name. We don't just call it diabetes. I'll refer to it as BTs, but if you had to write it in an exam, you would write diabetes mellitus. So there are two different kinds of diabetes, type 1 and type 2. So type 1 is due to an inherited factor or damage of pancreatic cells. Okay, so inherited factor or damage. So you were born this way. Mostly diagnosed in children and young adults. So what are some of the problems? Well, what is the explanation of this? The diabetes is caused when the pancreas stops producing insulin. It usually occurs in young people under the age of 30 and even smaller children and infants. It starts suddenly. One day you're just completely diabetic, like 100%. This type of diabetes is treated with insulin injections. And please remember, like we'll go over genetic engineering again, but the insulin injections actually come from bacteria that produce the insulin for you. The insulin intake must be balanced with a patient's diet and an exercise program. So you can't just, you know, take up this insulin, all of a sudden everything's fine. Like your body actually has to try and use the insulin. And that's why to a large extent diabetics actually, a lot of them will suffer major diseases, which we'll go through later, but it's just because they don't want to have a proper diet and exercise program. So diabetes type 2 is usually caused by obesity or poor diet and lack of exercise. So this is when you're a sloth, when you're a couch potato. You don't run, you don't stand, you don't walk, you don't even make your own coffee and tea. You just sit there and you do absolutely nothing. So this is more common in older people, and this can lead to you needing to take injections if you don't look after yourself. So can also be called pre-diabetic. This disease is caused when the pancreas does not produce enough insulin, or the insulin produced does not work properly. So to a large extent, remember, like from last year or grade 10 even, when I taught you about the fact that there are glycoproteins on top of all cell membranes. What happens is the insulin should actually attach to that glycoprotein, and then it indicates that you now need to absorb more glucose. But to a large extent, sometimes those glycoproteins aren't there, so that could be the inherited type, or it could just because your body doesn't produce it because you're becoming a sloth. Older people are usually affected with type 2 diabetes. These are over 40. All right, so diabetes type 1 under 30, diabetes type 2 over 40. This is a lie, because in modern day times, exactly what I'm doing now is sitting on the floor trying to keep upright, but I'm not doing much. And this is going to potentially cause, if I continue this for the next maybe a year or two, I would probably develop type 2 diabetes. People who suffer from the type 2 diabetes are usually overweight and don't exercise. So even the most simplistic amount of exercise is going to help you steer completely away from diabetes. But it also is not just the fact that you don't exercise, it also has to do with what diet you have in your system. So the symptoms of diabetes mellitus are very high levels of blood glucose, and if someone has diabetes mellitus, you can actually smell their breath, and their breath is extremely sweet. So let's say they've drunk water like half a liter, and they haven't had sweets for a bit, and they breathe, and you can smell sweetness in their breath. It might mean that they actually have diabetes. You'll also find that they have a lot of, there it is, B, there's glucose in the urine. So the body actually doesn't know what to do with this glucose, so it sends it to the kidneys, and the kidneys try and excrete it as much as possible. But this is ultimately going to cause an increased thirst, because if I'm urinating that often, it means that I'm losing all of my good water, and all that good water is going to cause me to be far more thirsty. I mean, these people chug like tons and tons of water. So this also, if you drink lots and lots of more water and there's glucose in the system, which is ultimately pushing all of your water around incorrectly, because if you have too much glucose inside of the nephron of the actual kidney itself, all the water is going to move inside of there, and then it's going to be pushed out of the urethra. Okay, so it's going to push out of the urethra. You're going to experience nausea and vomiting, increased fatigue, because your body's just not going to hold on to any of that glucose. So if your glucose levels drop, let's say for instance while you're sleeping, you're then going to wake up extremely tired. You could also experience weight loss, because remember, your body is not converting any of that glucose into fat, which is extremely necessary. So they're talking about weight loss as a problem over here. Like, we're not going to try and get diabetes so we can get skinnier. Then blurred vision, it affects the eyes extremely, and you're going to experience some really bad non-healing wounds. All right, now please do activity 3 on page 43 and 45, and activity 4 on page 46 and 47. Good luck. So I hope this has helped you guys explain the negative feedback system a bit more, and that you guys understand glucose, glucagon, glycogen, and insulin. So those are some of the things you need to go back, do all the activities, and if there's big problems in there, let me know. Have a good day, ladies.